In this problem, a rectangular box with a square bottom and no top is to have a volume of 864 cubic inches. Find the dimensions of the box that make its exterior surface area as small as possible. So my first step here is I'm going to designate variables. Let's call the side length of the box S. Since it has a square bottom, this dimension here will also be S. And the box will have a height. Let's call it H. There's some other variables that are important too. The area. Let's call this the exterior surface area. That's the thing we're being asked to minimize. And you could use V for the volume of the box. Okay, that's step one. Step two is to come up with any equations or relationships between variables that you think might be relevant here. From geometry, we have formula V equals length times width times height, but in this case, our length is side, and then the width is also S, and then we need to multiply by the height. So S squared H would give the volume of this box. We could also come up with a formula for the surface area of the box. Notice that there is a base which has an area of sides squared. And then there are 4 identical sides to this box, all having an area of S times H. But there are 4 of them. Okay, where does the 864 come into play here? Well, that's the required volume. So let's plug that in here. Then we can eliminate the variable V. A lot of times that's what you want to do, is get rid of any unnecessary variables. Alright, so which one is the constraint equation? That would be this one, because our volume is required to be 864. So this equation has to hold true no matter what the solution ends up being. That's why it's called constraint. And the other equation, because we're trying to minimize A, this is the objective function. Now, as is common with these, right now we have our objective function. It's a function of 2 variables, but we want to get it down to just one variable. So that's where we're going to use the constraint equation. Let's just solve it for one of the variables. Looks like the easiest one to do would be to solve for H. And now we'll want to substitute. Substitute the result we found in for H. Let's try it. Okay, we see now that our area function is a function of just one variable. We want to try to simplify it as much as possible here. We get s squared plus 3456 over s. All right. Next thing to do is to find out if this area function has a critical value. So let's get its derivative. We'll have 2s and then minus 3456 over s squared. We want to set that equal to 0 now. Now we'll try to solve for the s where the derivative is 0. So let's have 3456 over s squared equals 2s. Multiply to the other side, you get 3456 equals 2s cubed. And if you solve that, you find s equals 12. All right, so we should now find the height of the box. Looks like 12 inches is the ideal length and width of the thing. Let's find the height. Using our formula from the past, which says at h equals 864 over s squared. So that's going to be 864 over 12 squared. Which is 6. Okay. All right, what would be that minimum area then? Let's go back to the area function, plug in our 12 for the side, and then 6 for our height. I'm using the objective function here. So I get 432 square inches. Now, as it says, in order to prove that our solution really does yield a minimum surface area, we should use the first derivative test. So I'll do that here on the side. Okay. Our derivative of a, like the original a function was s squared plus 3456 over s. So our derivative was 2s plus negative 3456 over s squared. We said that there was a critical value at s equals 12. So let's just go ahead and put that 12 down. And then we can try 13. And let's try 11. So a prime of 11 is approximately negative 6.56. So we have a negative slope there. And a prime of 13 would have been approximately 5.55, which is positive. So through the first derivative test, it shows that there really must be a local min at s equals 12. It checks.